Hi everyone and welcome to EE326 Lecture 28. Today I'm going to be talking about zero cancellation, which has to do with canceling the right half plane zero that we talked about last time. I'm also going to introduce briefly a topic called power supply rejection ratio. All of these topics can be found in your book in section 13.1. Okay, so let's get started. Okay, as we discussed last time, the problem with the right half plane zero has to do with stability and phase margin. We see here, just as a refresher, we see that if we have our second pole omega p2 and we have this right half plane zero nearby, we can see that the gain actually slows down in its roll-off, right? Instead of following this trajectory like this, it flattens out a little bit from the zero. In other words, it doesn't get to this 0 dB mark as quickly. And conversely, the phase actually rolls off faster because of the 90-degree phase shift associated with the omega z and omega p2. And so in this region here, we're going down at minus 90 degrees per decade, whereas if it were just one pole, we'd be going down at minus 45 degrees per decade. And so we get a faster transition in the phase, which means we're getting very closer and closer to this threshold of 180, which is going to give us instability. Even if we're not unstable, it can also lead to a smaller phase margin, which, as we know, causes problems. So that's the challenge with the right half plane zero. And again, as a refresher, the right half plane zero comes from the fact that we added this compensation capacitor, which we needed to split omega p1 and omega p2. All right, so what is the solution to the right half plane zero? So one solution that we can do is actually add this resistor here, and I've labeled it as RZ. I think your book labels it as R, but I think it'd be clear to give it some subscript there. So we add a resistor in series with the capacitor CC. And this has the effect of moving the zero to a higher frequency. And in fact, as we'll show in a second, we can actually bring it all the way back and into the left half plane. Now, one of the problems with this approach is it's going to add another pole. You're adding another resistor, so we're going to end up with another pole in this. But generally, the pole that we're adding is not too much of a problem, but we do need to be aware of it because it can add some negative phase shift. So if we want to analyze this, it's instructive to look at the small signal model now for transistor M6 and M7 for the circuit. Keep in mind, this is the second stage, in case this wasn't clear. This is the second stage of a two-stage op-amp. So we're only showing the second stage transistors M6 and M7. All right, so if we wanted to create the small signal model, it would look something like this. We'd have our voltage-controlled current source from M6, and that would be GM6 VSG6. It's going to have some RO associated with it. That'd be RO6. This is going to be small signal ground up here. Then from transistor M7, this is only going to have a bias voltage on it, so there's no small signal there. So all we're going to see is RO7. We're going to see no change on the GM from transistor M7. And then we have coming in here, we're going to have a resistor and a capacitor. And this is going to be VSG6 as their input voltage. And so this is RZ and this is CC. Okay, so we can now analyze the circuit to try to figure out how we might pick this value of CC. Okay, so let's go ahead and do that. So what we can do, we've added this series R with CC, and we can move the pole out. The key observation here, if we want to quantify this relationship, is to say at the zero, we recognize that the voltage at the output should be zero. That's in fact what the zero means, right? We're not going to have any output voltage. So if we set the output voltage to zero and then use KCL at that node, we can find a relationship between RZ and CC. So let's go ahead and do that. we can do KCL, and we can say we could say the current flowing in our voltage controlled current source must all go through CC and RZ, because if we have 0 volts across uh, 0 volts across RO6 and RO7, we're not going to have no current flowing through them. So we could say that the current GM6 vs G6, well, that's equal to 0 minus VSG6. I'll just call that VSG6 over the series impedance here, which would be RZ plus 1 over SCC. So now if I solve for S, all right, I can find that S is equal to 1 over minus RZ plus 1 over GM6 times CC. So we can see that if we set RZ equal to 1 over GM6 such that the denominator of this equation goes to 0, we'll find that omega z, right, or S here, will tend to infinity. So if we set RZ equal to 1 over GM6, our 0 frequency will in fact go to infinity. And so what essentially that's doing is saying we're going to push that so far into the right half plane, we're going to push it so far out that it's effectively gone. And so if we wanted to visualize the effect of that, say in a Bode plot, it would look something like this. We have no 0 anymore. We have omega p1, our dominant pole. We have omega p2, which is from the second stage. We have this new pole that we've added from the resistor, right? But we have no 0 anymore. And so if we look at our Bode plot, we're still, depending on the separation of these poles here, omega p2 and omega pz, we're still going to have this minus 45 degrees per decade roll-off, right? And this is basically from this section here is from omega p1, and this section here is from omega pz. So we pushed the right half plane all the way basically out to infinity, but we did add a new pole, but this new pole tends to be at high frequency. Now, in terms of a complete solution to this, it is possible. So we could, again, draw the small signal model like we've done before, using these GMs, Rs, and Cs, except we've now added this zero canceling resistor here. And we could do KCL at these nodes and solve for the relationship between the output and the input. We end up with 1, 0, and 3 poles. It's pretty messy, but it is possible to do, but we can get a lot of the information just by these approximations and looking at individual nodes, right? And again, it's important to keep in mind that this new pole, omega pz, it should be significantly higher than the pole at the output, omega p2. All right, so let's talk again a little bit more about controlling omega p2 in this situation. Let's assume that the new pole we've added is much larger than omega p2, right? So it's way out here somewhere. We're not going to have to worry about it so much. And what we'd like to do from a phase margin perspective, right? We've discussed this before, is we need to keep omega p2 greater than or equal to, should be greater than or equal to approximately 3 times the omega unity loop gain, the unity loop gain frequency. And that's for a 70-degree phase margin. So if this is omega UGF in here, or omega T as your book refers to it, we need this distance here to be about 3x, right? That's for 70 degrees. And so we can figure out these basic relationships, for example, what the omega UGF or omega T is, right? If we assume it's a single pole system, we can write this equation for a single pole system, which comes directly from here by looking at the magnitude. If we set the magnitude equal 1, and we say that omega UGF over omega P1 is much greater than this one here, then we get this relationship that the omega unity gain frequency is about the low frequency gain A0 times the first pole, omega P1. So that tells us that omega T, right? Again, this is omega T in your book, that the omega unity loop gain, actually this is more having to do with the loop gain, right? So if you look at the loop gain now, we're including beta, then it's going to be beta times this omega UGF. Okay, so if we have feedback and we're including the effects of beta, we need omega P2 to be approximately at 3 times beta A0 omega P1. Most of that should be review at this point. Okay, so we can use this information to help us design, help us pick a value for CC. So let's walk through how we might do that. Okay, so we just mentioned that for a 70-degree phase margin, we need omega P2 to be greater than or equal to 3 times the unity loop gain frequency. So let's figure out what this unity loop gain, an equation for, we're going to figure out an equation for each side and then relate them, and we can figure out, then we can determine how large the compensation capacitor should be. So omega T, again, I'm going to repeat this, but omega T, or the unity loop gain frequency, unity gain frequency, is A0 omega P1. And then, so if we substitute in A0, we substitute in omega P1, we get that omega T is GM1 over CC, right? That's, so we can then write that the omega unity loop gain, right, that's equal to beta times omega T, is equal to beta A0 omega P1, so that's equal to beta GM1 over CC. Again, this is just substitution, right? We're just taking, we know this relationship, right? Because now we're in feedback, so we have to multiply everything by beta. Keep in mind, beta is less than 1, right? So this is the situation where our Bode plot is going from here down because we've multiplied it by beta, and you can see that omega T goes down to what I've labeled as omega unity loop gain, right? So this is beta A0, and this would be A0. So you can see why the first pole, or the unity gain frequency, moves down. Okay, so that's the relationship between the omega unity loop gain and CC. So omega unity loop gain is equal to beta GM1 over CC. All right, so we have this relationship here. Now, what about omega P2? Well, we know from our earlier derivations, you can look at your notes, that omega P2 is approximately equal to GM2 over C2. Okay, so let's relate them now using this same inequality on the top, and we'll find that GM2 over C2 must be greater than or equal to 3 times beta GM1 over CC. So we just substituted in here and here, right? And we get this relationship. And now we can see if we solve for CC, we get CC must be greater than or equal to 3 times C2 times GM1 over GM2. And now if we substitute in the small signal GMs from the transistors, we'll get this final equation that says 3 times C2. This would be GM, little gm now, 1, 2 over GM6. So this is a nice design equation. It says that if we have these certain values of GM and we have a certain load capacitance or total capacitance at the output node, C2, then we can determine what size compensation capacitor we need for a 70-degree phase margin. Obviously, we could choose a larger compensation capacitor and get a bigger phase margin. But this is a nice guide into picking the size of the compensation capacitor. Now, that's not all we can do. So what we talked about so far is taking this 0 and moving it off into infinity. In fact, what we can do is we can actually, if we keep moving that 0, it'll push it back into the left half plane. We'll push it all the way around into the left half plane. And we'll see what that quantifies to in a second, but we can actually push the 0 to the left half plane. And you might ask, why would you want to push the 0 to the left half plane, which is a good question. What we can do is actually align the 0 with the second pole frequency and effectively turn our system into a one-pole system. So you can see this in the Bode plot. If the 0 and the second pole line up, right, we have no change in the slope of the magnitude, right? And we also have, we'd have a minus 90-degree phase shift in the phase from omega p2, plus 90 from omega z, because it's a left half plane 0 now. And we end up with no change in our phase, so our phase margin would be 90 degrees. Now, I've ignored the new pole from RZ, so if we had another pole out here somewhere, right, then we'd end up with some small change, which might contribute a little bit to the phase margin, but not much. So this can be an effective way to really to create a robust phase margin by pushing the 0 all the way to the left half plane. All right, so how would we figure out what value we'd need? Okay, so we talked earlier about omega z as equal to this value, right, from our earlier derivation. So if we want to cancel the second pole, we want this 0 frequency, not to be infinity anymore, where 1 over gm6 is equal to rz. Now we want this second pole location, we want to set that equal, this 0, we want to set it equal to the second pole. And you remember that omega p2 is approximately equal to gm6 over c2, right? And so if we set these equal, basically set these equal, and then we solve for the rz that we need for this, what we end up with is that rz is equal to c2 plus cc over cc times 1 over gm6. In that case, we could actually completely cancel the pole, our second pole, and we'd be left with a very robust phase margin. Now, this is a nice concept. However, it is subject to movement, because we can't quite predict, there's variation, for example, in the resistor. So in practice, it's difficult to cancel that second pole over all the process corners. That is, when the transistors and the resistors vary a little bit, and the resistors actually can vary substantially, we're not going to cancel it quite as exactly as we would like. With resistors, as I've told you in the past, we really can only count on the ratio of resistors, not so much their absolute value. In addition, by adding the resistor, the resistors themselves can take up quite a bit of chip area. So in practice, the way this is actually implemented, if you looked on chips, how they do this is they add a transistor, not a resistor. And they bias this, they provide a bias voltage to make that transistor operate in the triode region. So this is really acting like a resistor to provide the cancellation. But again, due to process variation, we're going to get some movement, and you can't actually cancel the 0 very reliably. But even if the 0 and pole 2 are not exactly canceling, what you'll see here is that we might get some small phase shift because they don't cancel, but generally it's going to be small, and we're still going to be left with a robust phase margin. So in practice, this technique is used all the time in two-stage op-amps to either cancel the second pole or take the 0 and move it out into infinity. Okay, so one other concept that I would like to talk about today before we finish is this concept of power supply rejection ratio. It is in your book. You won't be tested on this, but I think it's something you should be aware of. So this is an issue when we have noise on either the positive or negative supply or both, and the noise can couple in through the transistors or through capacitors into our circuit at the output. And this is more of a problem in mixed signal circuits. And what we mean by mixed signal circuits, those are circuits that have both analog and digital circuits on one chip, which these days is very common. The reason this is more of a problem is that digital circuits, which have large switching behavior between VDD and ground, cause large spikes or noise in the power supplies because they either consume a lot of power or they dump all this current into the negative supply. And so if you have an analog circuit that relies on small signals and the supply is jumping around all over the place, it's important that this noise doesn't couple in too much to your output. And so power supply rejection ratio is a measure of how much the noise can couple into the output, effectively the gain from the supplies to the output. And so what we'd like to do is keep that rejection high so we can reject most of the noise from either the positive or negative supply. So there's much more written about this in other textbooks. We're not going to cover it in great detail in this class, but it's something you should be aware of. You will see PSRR referred to all the time in data sheets, so it's something to be aware of. Okay, that's it for this lecture. Thank you very much.